When organic students first learn about SN1, SN2, E1, and E2 reactions, it can be a bit daunting and overwhelming because there's so many different reactions happening with basically the same thing. You have a carbon with a leaving group attached, and then you have something else that's going to attack as either a base or a nucleophile. So which one does it do? What's your major product? That can be really hard for students. So today we're going to delve into which one is major and why. Really what it all comes down to is the energy of each different component. Now we're going to look at this through basically 5 lenses. We're going to look at it through the alkyl halide, or of course leaving group connected to the carbon. So is the carbon primary, secondary, or tertiary? So alkyl halide is going to be where I'm usually going to go, but of course really that could be any sort of leaving group that we have. Second of all, we're going to look at it through the lens of the nucleophile or base and its size. Is it bulky, or is it really small and narrow and able to just get into tight spaces? Then we're going to look at it for nucleophile or base strength. Is that nucleophile or base really, really strong or weak? For example, an alkoxide, an O negative with a negative charge would be very strong, whereas the alcohol, which is the protonated form of that, would be weaker. Then we're going to look at temperature effects. What would temperature do to this whole situation? Which one would temperature make dominant and why? And lastly, we're going to look at solvent effects. What do solvent effects do to this whole situation? So, first of all, let's delve into it. And I'm going to look at first order reactions. So if you're looking at a first order reaction, it's first order because there's only concentration of one thing in the rate law. If we look at our alkyl halide and our leaving group, let's say for example on the alkyl halide would be our halogen. So if we look at that, there is nothing attacking. We just have our leaving group leaving, and now we have a carbocation left behind. That carbocation, of course, would then in the second step be attacked, is what's going to happen. Now, what makes this stable? If we look at primary, it's very, very, very unstable, because as our leaving group leaves in a primary, we only have hydrogens attached and there's nothing to stabilize that empty p orbital that's just lonely by itself and incredibly positive. Now, if we look at putting carbons all around, each of those carbons is going to have a CH bond to it. And those CH bonds nicely align with that p orbital and hyperconjugate. Hyperconjugation is when we donate electrons from those bonds and those electrons kind of fill in that empty p orbital. We have 9 of those bonds all able to hyperconjugate and stabilize that. So a tertiary alkyl halide is going to be more likely to form a carbocation. A second order reaction happens, on the other hand, when we have the leaving group getting pushed off by that nucleophile or base. That's because a second order reaction in the rate law has both the alkyl halide and the nucleophile or base in the rate law, second order, because both are first order. It's first order to each one. So what's going to end up happening in that case is we're going to have our nucleophile or our base. Let's look at the nucleophile because it's probably the best example, is going to come and put electrons into the sigma star or antibonding orbital. As it puts those electrons into the antibonding orbital, it's going to push the leaving group off. This can happen unless we have too much substitution. So if you replace the hydrogens in that primary alkyl halide, turn it into a tertiary alkyl halide, now it's got all these C groups, which of course have all their hydrogens on them. It's so bulky that those electrons from our nucleophile or base just can't get in there to attack. So what this ends up doing is preferring a less substituted product. So what we see is that to get a second order reaction, we need less substituted. However, to get a first order reaction, we actually need more substitution to stabilize that carbocation. So these two things are diametrically opposed. This is really nice because it shows us why and how a tertiary is going to favor, of course, a first order reaction, whereas a primary is going, or even secondary, will favor a second order reaction with that attack happening at the same time. So now to address the size factor of the nucleophile or base. As we talked about at the beginning, there is a size factor involved here. Now, really when we say nucleophile or base, we are saying that if it is a base, it can go attack a hydrogen, whereas if it is a nucleophile, it can go and attack the carbon and push that leaving group off. So when we're looking at this, if it's really, really bulky and big, it's going to want to go take a hydrogen, because since it's so big, it's easy for it to go grab a hydrogen that's just sticking off. Whereas that carbon is tetrahedral, so there's all kinds of stuff around it that it has to get in between to go grab that carbon. Now, if it is small and narrow enough to be able to go get that carbon, that was what it would prefer to do, because that carbon is quite positively charged, because the leaving group is quite negatively charged. And so it creates a nice charge separation there, and the nucleophile would love to attack that and grab that carbon, pushing the leaving group off. Now let's talk about the nucleophile or base's strength, the third factor, and how this plays into it. For this, we're going to lean pretty heavily on your prior chemistry knowledge. From your prior chemistry knowledge, you know that things, for example, like hydroxide, OH-, is a way stronger base than H2O, water, because hydroxide is negatively charged. So this is the kind of knowledge we'll lean on. Now, of course, that also means hydroxide is a way better nucleophile, because the stronger base is also a better or stronger nucleophile. These things go hand in hand. Now, where can the strength of the base actually differentiate in that case between substitution or elimination? Because shouldn't it not differentiate if base and nucleophile strength go hand in hand? Well, the best example I probably have for that is a tertiary alkyl halide. Now, if we look at a tertiary alkyl halide, what is possible for it to do? Well, it's tertiary, so it cannot do an SN2 reaction. The backside attack is blocked. It can do an E2 reaction, however, because the protons are still sticking out. They are not blocked in any way. So that really strong base could grab a hydrogen, do an elimination reaction, kick off the leaving group, and we form an alkene. Now it can also do an SN1 or E1 reaction. So we could also, because it's tertiary, have our leaving group leave, form a tertiary carbocation, and then we could grab a proton, do an elimination, or do a substitution reaction. Well, it turns out that if you get a stronger and stronger base, which one would it push towards? Well, this is where we have an interesting thing. We have to go back to what a first or second order reaction means. In a first order reaction, our base or nucleophile isn't even involved in the reaction. Therefore, if you have a really strong base, it actually has no effect on the product. The leaving group has to leave before that nucleophile or base can do anything. Whereas in the E2 reaction, the strength of our base actually pushes the reaction forward as well as the alkyl halide. So if we get a really strong base, it can speed up that reaction. Whereas it would not speed up our SN1 or E1 reactions. Therefore, it would push towards elimination if we have a stronger base and a tertiary alkyl halide, because that stronger base is only going to affect the second order reaction, which is E2. And remember, SN2 can't happen because the bulky backside is blocked. Our fourth factor that we're going to look at, of course, is temperature. For temperature, we're really going to need to take a closer look at elimination reactions and one important factor involved in them. So if you look at an elimination reaction, remember what we have is a base, and then we have an alkyl halide. That base is going to attack the alkyl halide's hydrogen, and the leaving group is going to leave. Now, if we look at our products, that means that we're going to have a base that's now protonated, an alkene, and finally our leaving group that's all by itself. Now, if we count these, that means that we had 2 reactants, and we now have 3 products. If we remember entropy from our general chemistry, this means that we have an increase in entropy, or an increase in microstates, because we now have more things involved. We took 2 parts and made 3 parts. That always is an increase in entropy. If we look at our Gibbs free energy formula, delta G equals delta H minus T delta S, we notice that the temperature factor is multiplied by the entropy. So if we change the temperature, it changes how much that whole entropy part affects our energy. Because our entropy is favorable here, if we increase the temperature, we're actually increasing the likelihood, or the free energy we're gaining, from producing an alkene rather than a substitution. If you look back at a substitution, you'll realize that the reactants and products, we have the same number of them. So there is no real entropic benefit to doing a substitution relative to an elimination where there is a large entropic benefit. For this reason, if we run temperatures hot or warmer, we're more likely to produce elimination reactions. We need to talk about our 5th now and biggest topic, which is solvent effects. This is really the biggest topic because it tends to be the most complex for students to understand. Solvents have actually a significant impact on what the reaction does. Now, we're going to be talking about polar solvents the whole time here because we're going to use polar solvents. Since we have charged or relatively polar with these alkyl halides or these leaving groups, we always have very polar bonds. So these are going to be polar reactants, therefore we're going to use polar solvents to dissolve them. The question is, are we going to use polar protic or polar aprotic? Polar protic solvents are going to have a proton or a hydrogen bonded usually to an oxygen. Essentially think of anything that hydrogen bonds here. Polar aprotic solvents do not have that. Now, the reason we talk about this is hydrogen bonding, if you remember, is just a really, really strong dipole-dipole interaction. That's because hydrogen bonded to an oxygen or fluorine or nitrogen produces a very polar bond. So we also need to kind of review reaction energy diagrams. So if you look at a reaction energy diagram, what you have is the energy of a reactant and the energy of an activated complex. And that sort of difference in energy there forms your activation energy, or the hill you need to get over for the reaction to then progress automatically. Well, if we're going to look at this, we need to also think about our first and second order reactions in here and kind of look at what's going to happen. So we'll do that in a minute. Now, if we lower the activation energy of our activated complex, what's going to happen? Well, it's going to actually decrease, and then by the way, lowering energy means to stabilize, right? And that's going to decrease our activation energy, which is going to speed up the entire reaction. Well, let's look at how this could potentially happen. If you're looking at a first order reaction, well, it turns out that what it's forming here is a carbocation. And then, of course, it will go on and do E1 or SN1 reaction in the latter part. But at the beginning, it's going to form a carbocation here. Now, that carbocation can be stabilized. Well, let's look at how. And notice the carbocation is charged and the starting group isn't even charged. Well, if you look at this, what we're going to have is we're going to have a carbon with a leaving group, and once it leaves, you're going to form a C plus, a carbocation, and the leaving group is now going to be negative. Well, if you took a really polar molecule like water and you surround that carbocation and that anion, that whatever leaving group was, it's really going to add to its stability, but it's not going to add too much to the stability of our starting materials because we don't really have anything that's charged at the beginning. Now, if we go back to this reaction energy diagram, let's look at a second order reaction. Well, a second order reaction has a really strong base or nucleophile. That's what drives it forward and makes it happen. And that's usually negatively charged. And that's going to attack, and in our activated complex, we're going to have kind of a big thing where we have our nucleophile attacking and our leaving group leaving all at the same time, and we're going to eventually after that yield our new product where we have our thing that attacked our nucleophile now bonded to the carbon and the leaving group has left. Well, if we look at this and look at the solvation of it, if we look at our carbon and leaving group and our nucleophile and we surround it with solvent, well, where is it going? What's it going to do to the stability of this? Well, as we can see, it's really going to increase the stability or lower the energy of this reactant or the nucleophile. It's not going to have that much effect, however, on our activated complex. Well, if we go back to that original reaction energy diagram, what would happen if we lower the energy of our reactants? If we lower the energy of our reactants, as we can see, it would increase the activation energy. And increasing activation energy would slow down the reaction. Therefore, this would lead to a slower reaction with a very polar solvent. So now we can see why a polar solvent would actually slow down a second order reaction and speed up a first order reaction because of adding that stability. This is something we can really use if we want to, for example, push something towards first or second order, which sometimes we do want to do.